Okay, so then this is the integral approximation, but as you saw, we still have some derivatives to also compute during this. So now we're going to introduce a big Dij, which is a matrix, which again can be pre-computed. This is then dx of Lj of xi. Or in our case, instead of xi, it's going to be xi I. But this is just general again. So this matrix here can be defined well by using some algebra, which I will just skip. So Dij is some constant Bj, which you also can pre-compute over the I. 1 over I minus xj, and these are then the, this is a arbitrary point. No, this is a JLL quadrature point, this one. Yes, where we have that now Vj is the product I equals 0, I must equal j of j minus xi, and then the inverse of this. And I've got to mention that I is not equal to j in this regard. So this again can be pre-computed. So again, yeah, if you just change the j with an I, then you will get a formula for this. So both of these can be pre-computed. So I'm going to call it pre-computable. Meaning that we only have to solve this once. And then we can just look up in a table. And that saves us for a lot of effort or just basic numerics. Again, we can then use this on the integrals. No, not the integrals, the integrals, the weak form of the wave equation. So what we get then? Well, we get something that is going to look ugly, but you'll see that we can clean it up quite a bit after a while. I.e. Again, this is temporal, but I'll skip it. And then instead of the integral this time, we are doing the JLL quadrature. K rho bar of xi k l j of xi k li of xi k again dx over the at the point k, and then similar. So now if you compare this with the previous form, you see that we have replaced the integral with the sum. And then all of these are just points. So these are the GLL points. These should probably write that up. GLL points, because that comes into play later. Again, the next one, you've seen this before. I, E, K equals 1. Again, at this one, because that's the amount of basis functions you have. This weight of K, mu bar psi k psi l j of psi k d psi li k. You have to do this and also this one. Psi that's psi k. So everything of this can be computed. And then also for the source term. K equals 1 and plus 1. The kth weight k bar of psi k t dx d k. I think that is all. But these have a property. This is sometimes called a cardinal property. That is, this is only non-zero when these two indices are the same. This is equal to the delta function, sometimes called. Or the Dirac's delta, I guess. So this is 0 when I is not equal to k, and 1 when I equals to k. And do you see something we can do with the formula then? Something that disappears? Well, if you take a look at this sum. So when, say this is, well, 1, then this is only non-zero when j equals 1 and k equals 1. But then if I is something else, then the whole thing is just going to be 0 again. So using this property, you see that this is equals 0. No, it doesn't equal 0 only for when j equals k, and the same goes for this bit, that this is only non-zero when I equals k, and then the same goes for this and this. So that means we in essence don't have to do this sum. Yeah, and for completeness sake, also this. Does that make sense? Any questions? This is kind of the turning point of the spectral elements, that you can actually neglect the, well, you can apparently neglect the integral because you have this nice property of the Legendre polynomials. So, what do we end up with? Well, let's see. We get. So now we can skip these sums. I might need more space though. Still have these and 4 coefficients. But the sum is now, well, gone, but it's not there. And Cj delta ij, which means that we can actually remove some of this sum as well, if you want. And this is the illustrated point. Yes. Okay, yeah, because these are derivatives, so we still need to complete these. Some of them, at least. Okay, new. I please bear with me. X squared x t psi. Okay, and next we will rewrite this on a matrix form. So the point of J F bar J T dx d J. So and now we can have this on matrix form. So this bit here, this is going to be a diagonal matrix. Why is it going to be a diagonal matrix? Because of this term. So we're going to call this M shine J E E. And then we have this thing here, which is a bit more complicated, but we do have a lookup table for it. K J E, and then we have the driving force. Just F J E. Can you see this down there? Okay, good. So due to this nice property, we have a mass matrix of just diagonal elements. So let me just rewrite this matrix equation. Still need to figure out these temporal expansion coefficients. Double dot I E T J, oops, J I, the element E plus spring I E T K J I E, and then F J E is just a vector. And then again, we have kind of, well, it is kind of like cheating because we have masked a lot of complexity within the matrices, especially this K matrix. The good thing here is that, well, this expression, or, well, in fact, this expression, this holds for all of the elements. So that's good, because we have this transform back and forth. And also, again, this one is going to be diagonal, so it's trivial to invert. How do you invert a diagonal matrix? You just take the inverse of each of the diagonal elements, which is a pretty basic operation. So, good. So that means that it's very easy to find an explicit formulation for this UIE double dot, since MJIE is diagonal. But we still have to stitch all of these together. So we need a global solution. So I'm just going to make it easy now. So now we have split our main G into two smaller ones, G1 and G2. And then when we label these points, well, they're going to be labeled as 1, 2, 3, 4. But when we stitch them together, well, we'll only have 3 points. And 3. And then if you have more points, I mean, these are the GLL points, then you would get, well, different. So instead, if we had looked at the ones where you had positioned it differently, so 1, 2, 3, 4, 5, 6, 7, 8. Well, 1 is going to be mapped to 1, 2 is going to be mapped to 2, 3 is going to be mapped to, well, 3, but then 4 and 5 is the same point. And then 6 is going to map to 7, and 7 is going to move up to 6 here, and then again 7, oops, 7 here. So see, you have to keep track of what you're doing all the time. Another kind of challenge by implementing the spectral element method. So, well, the mesh is difficult to create, and the bookkeeping is also difficult to maintain. But when you get all of this working, then you have a very powerful method on your hands. But so after having solved this, we have to assemble. So we have to assemble the local, these MEs, ME, and we are going to call this MG and KG matrices, where we are taking into account this. See, Yes. So exactly how to do it, well, that depends on, well, how you want to do it. So it's more easy in 1D because then you only have like the number line, but when you have in 2D, as we will do, I guess we can start doing it at least, then you would have, well, what comes after 1 when you have a mesh looking like this? So if you number all of the elements 1, 2, 3, 4, 5, and 6, then you have to keep track of which elements are neighboring to number 4, which are neighboring to element number 2. Well, that's 1, 3, 4, and 6, so it's only a neighbor of 5. So there's a lot of bookkeeping going on here, which is why you need to keep track of everything. But we can, yeah, in this case you basically just sum these two, and then you get it. But I won't go into more detail on that topic. So does it look overcomable to actually program a spectral element method, especially in the 1D case? Do you think you could do it? Do you want to do it? No, usually you have a software team that actually prevents these and does it for you. But it is very good to know the workflow of it, so you know what can go wrong. So as I briefly mentioned, that one of the biggest topics here is actually creating the mesh. So first you have to do the meshing. Well, this is actually its own topic of research. How to create the best possible mesh. This is actually ongoing research. We don't really know how to quantify what is the best mesh for a given problem. Topic of search. So it's actually challenging to create. So I'm not sure if some of you are working on projects where you have to create a part in, for instance, SolidWorks, and then you can import this 3D model into a finite element solver. Maybe it isn't the spectral element method, but some kind of finite element method. And then this program will break down your shape into a mesh that actually suits the computations you're doing. If this meshing is wrong, well, if you remember the first lecture, then you can get oil patterns that just end up dead or upside down in the ocean, and millions are lost. So this meshing is important to get correct. It's very important to get correct. I mean, you can do it in a brute force method and just have a very, very fine mesh, but then, I mean, your result is going to be accurate, but it's also going to take forever. So then, well, you have to find a middle point. You have to have a coarse enough grid that you actually have time enough to do the computations, but it also has to be fine enough in order for you to get accurate results and not end up destroying equipment for millions and millions. And if you're to do this, there is specialized software to actually create the meshing. Well, So that's meshing. But now when you have the mesh all done, then you have to solve the equation. Solving the equations. Well, as I touched about, you have to have this numbering or bookkeeping between the local numbering, which is the one up here, and the global numbering. That can be different. That is going to be different. Scheme. And then, well, in each time step, you need to communicate between the local nodes and actually expose them to the rest of the system. So all of these solutions are, well, they're interacting with each other. So in each time step, we need to, well, because each of the elements are interacting with each other, so we need to update each element with information from the global system. And then, well, if we have the equation, then we need to solve it. Well, we need to solve it. Locally, and then assemble into the global one. And, well, actually solve the global system as well. To make sure that it all makes sense. So then we'll try to scale this up to 2D. Or any questions?
What do you mean by solving the global system?
Let's see. So you need to make sure that it's basically just scaling everything in space. So performing this inverse transform. So it should be easier to do. Because you are, well, I guess this is basically the same. But you have to assemble them. Then I mean that you have to go from this local system to the global one. And then when you want to output it in a meaningful way with normal, instead of just these reference elements, then you need to scale them back such that it makes sense. Such that your plotting makes sense. Let's see. And it's not that difficult to do in, again, 1 dimensions, but 2 and 3 dimensions. There's a lot more going on. So then we're going to try this with the isotropic elastic equation method. So we're going to define and x and a t. Our space now is going to be called, instead of g, omega, and big T, so this is time. It's only reals, so let's say this basically means that it's a 2-dimensional, this omega is 2-dimensional and time is just 1-dimensional. And everything is real numbers. But for those of you who did the elastic wave equation, if you're tired of seeing this equation, of t, so this is the x component of the displacement, dx stress x x t plus dy sigma x y plus, if we are getting it a force source, y component plus dx x of t. And then we have all the stresses. Sigma, let's see if we can do it over here. Sigma x of t, sigma y, and sigma y, and sigma x y. So x here is the xy coordinates. We're using the so-called Lemay parameters of x dx t again lambda x dy t. This one is similar. X. So this is x and this is y. Y. T. Oops. X t, and the last one x. So for those of you who try to implement boundary conditions and the elastic wave equation, well, in the spectral element method you get it for free, so you don't have to worry about perfectly matched layers and stuff like this, which is not part of the curriculum also. So does it look correct? It's basically the same formula as in the project text. And then the boundary conditions. This is the normal vector of the stresses at the boundary. So this means at the boundary of our omega, so partial omega, that means the boundary. So for instance, if this is your omega, then delta omega is this, or partial omega is the frame. So again, initial conditions equal to 0. Everything should start nice and quiet. Zero. And then we can get a weak formulation of this, if we have time. Yep. So if I can just write a weak formulation, we could stop there. So instead of GE now we're only integrating over. So am I going to weak?
Yeah, sort of so.
Okay, yeah. You can just disregard all of these, then it takes a lot. I mean, if you just think that, well, the displacement and stresses, they should be a function of space and time, and the model parameters, they stay quiet in time. I mean, you don't suddenly change the Earth during your simulation. You could do it. You have to do this in earthquake simulations, but we are not doing an earthquake simulator. We're not changing the ground. We're not changing a model by time. And again, this is optional source terms. You can also play around with introducing a stress source instead of a force source with these, as some of you asked during the project. Well, we have these formulas. Now we have to do the same as what we did with the 1D scalar wave equation. We have to find some kind of test function, call it psi, which I've done in my notes, and then integrate over space again. So space here is omega instead of g. So we have rho. So this is only the first one. See, this is my test function. dx x psi plus d y sigma x y c plus x psi d omega. Like so. And then we're going to do partial integration again. So with only integrating over the outermost layer, dx. So yes, this is how you're integrating over x and y, d sigma. So when you're doing the partial one, you can actually split them. So you have a dx integral here, and then a dy. No, yeah, a dy later on. Oh, sorry. Partial. psi t omega. Like so. And then in a similar fashion, this one will be 0 and this one will be 0. Why? Well, because of this. So this n here, that's the normal, the surface normal. So in this case, n is gonna stand like this, meaning that it would have no flux for that area. And then I guess the last thing I'm going to do is just write out the full formula of that. And then I'm not going to do this for all of them. Let's see. So then we have. Oops. Rho psi equals, well, both of them are negative. Psi x t psi plus psi y t y. Oh. Let me double check. Yep. Y t. That's the source term. Sigma. Or we could move this over here. So I think I just start there next time. And then that is also going to be the last topic of this course. How to do this in 2D. And I'll try to get a small demonstration how it works in 3D up and going. If I can get it to work. Hopefully I'll be able to get it to work. I'll try to have a meeting in the reference group, hopefully this week, if not then the beginning of next week. So if you could send them feedback or just to me directly, then we can discuss it. So it could be the lectures, exercises, projects, me as a person, I guess. Well, everything. And then I hope the project went well. And so I think almost all of you delivered, so that's good. There were some issues with Inspira, but that's not your fault. So everybody who delivered, even if it was a bit late, then it went okay. So no worries. Yeah, any questions? No? You seem eager to get home.